Cybersecurity and privacy breaches is a growing concern across the world today. The average cost of a breach as of 2020 was roughly $3.92 million, and for a large business would be well over $150 million. There is data inherently hidden in each one of us, and everything about you, whether it be your phone number, your age, your height, your email address, or your favorite food, is data that other organizations want to know and mine so that they can sell things back to you. The other use case is the data actually gets into the wrong hands, can be altered before it reaches the right destination, and can have tremendous effects on organizations and people. What if I told you there is a way to keep your privacy but at the same time mine data? If you're interested, keep watching. So let's go through how this actually works. Picture you have a customer ABC and you have a company XYZ. Now, company XYZ offers services, machine learning modeling services in more particular, that enable a customer to send over data that may be encrypted, and it allows them to take that encrypted data, do some machine learning against it, not have any visibility to it whatsoever, and send it back to the customer encrypted still, and only the customer can really unencrypt it. So let's see how this works. So I have a customer today that has some kind of data, and we'll walk through some of the data that we'll be looking at, especially for this basic toy machine learning model that we're going to build today. So the customer may have some vectors, or they may have specific data that they want to run against the machine learning model. They're going to take that data and they're going to encrypt it with their public key. And this goes back to asymmetric encryption, where you have a public and a private key. The public key can be shared with anybody, but the private key can only be shared by the person, in this case the customer, for them to unlock that data. So they're going to go ahead and encrypt it with their public key. They're going to take that data, then they're going to go ahead and send it over to company XYZ, but it's encrypted. So we'll take a look at that actually in code to see what it looks like when it is encrypted. Company XYZ is then going to take their machine learning model and they're going to apply it against this encrypted data. What that's going to allow them to do is, after that's done, they're going to be able to come up with some kind of a result that's going to be encrypted as well. So they have their machine learning model they run in the background. Even though the data is encrypted, they'll be able to give some kind of result back to the customer. That information is then sent back, still encrypted with the public key, back to the customer. The customer then takes their private key against that encrypted data, and they unencrypt it, or decrypt it in this case, and then are able to see that result. So we're going to build this transaction out actually in Python. I'm going to walk you through the code to see how we're going to be doing it. We're going to use a couple of basic libraries, so it's not going to be overly complicated, but we'll go back and look at this step by step to see exactly how it's done. So let's get started. So very quickly, you can do your research on basically what homomorphic encryption is, but for it to fall under the PHE method, really two properties need to be true. One is, if for example that I have a variable that is encrypted like A and another variable that's encrypted like B, if I add them up in ciphertext, which is basically encrypted text, and then de-encrypt it, it's going to be equal to A plus B. The other property that's true with partially homomorphic encryption is that if I take a ciphertext variable and multiply it by a scalar vector, after decrypting it, it's going to be the same as A times a scalar. So that is basically the properties behind it. So this really enables us to build what I would call sort of basic machine learning models. Now, if you want to go into more complex models, you really have to go into fully homomorphic encryptions. And, that's maybe something for another video. It's a little bit more complicated than this, but, there are some pioneers out there. For example, Paillier has got some implementations out there that you can download. IBM has one. And one of the more popular ones is by Microsoft, which is actually called Seal. And there's a Python version called PySeal, which you can go check out as well. There's a Docker image for it that you can open. So when I really look at the example that we want to go through today, it's something very, very basic. What we're trying to do is we're trying to predict somebody's salary based on some numerical facts about them. So first, we're going to be looking at their age. We'll be looking at their active lifestyle to see whether they're active and whether or not they're eating healthy as well, and as well as their gender. Now, in reality, you'd be looking at a multitude of other variables, but just for the purpose of this, like I said, we're going to be building a toy model. These are the 5 data points that we have, and we'll be using 4 of them to do a prediction against salary. And again, for the purpose of keeping this very simple, we're going to be using a linear regression model that we're going to go ahead and build in Python. So let's get started. All right, so one of the first things we're going to do is we're going to go ahead and open up a new file called linmodel. In linmodel, I'm going to be importing a whole bunch of different dependencies from pandas, numpy, PHE, more specifically the Paillier method, sklearn, and in sklearn we're going to be using the linear regression model, train test split, mean squared error, and r squared. I'm going to go ahead and create a class called linModel, and that's going to be my linear model. So get results is essentially going to read my data. It's going to create my linear regression model. It's going to create my test and train split. Then I'm going to go ahead and fit my test data against my linear model. And then I'm going to go ahead and predict my train split, which you'll see coming up very soon as well right here. Once I have that, then I'm going to go ahead and look at a few different metrics like root mean squared error, and as well as the r square. And just to let you know, I looked at the r square as about 0.84 or so. And again, I'm not looking for perfection in this model. It's just sort of a toy model at this point. The more important thing is to get these coefficients or the weights of the actual regression model. And that's what I'm going to be using against my encrypted data. So very soon, in just a quick second, I'm going to go ahead and print these coefficients. And these are the 4 coefficients that are going to correspond to my age, my healthy eating, my lifestyle, as well as the gender as well. So these coefficients are the ones I'm referring to as right here. All right, so that really completes my ML model, the one that the organization is going to be using, and we just created that. The next thing we're going to do is we're going to go ahead and create some simulated data for the customer. Then we're going to create an instance of a public and private key, and we're going to encrypt this data with a public key. So let's go ahead and do that next. Okay, first we're going to create another file called customer.py in this case, and this is going to be the customer's file. In here, we're going to create a method called store keys, and in there, we're going to create an instance of public and private keys generated by the Paillier key pair. I'm going to go ahead and store those keys in a dictionary called keys. If you're wondering what the NP and Q are, go ahead and look up the Paillier method, and you'll sort of understand what those stand for. Then I'm going to go ahead and store those in a file as a JSON file. I'm going to go ahead and run this function so that I can generate my keys and store my keys as well. So let's go ahead and do that now. All right, once that's done, let's get rid of this. Now I'm going to create a method that's going to allow me to retrieve those keys whenever I need them. So I'm going to go ahead and open up that keys file. Notice you'll see this says keys.json. It should say cust_keys.json. So this is an error that gets corrected later on. But it allows me to go ahead and pull my public key and my private key as well. So just make sure you make that change, and it returns your public and private key. And next I'm going to go ahead and create a serialized data function, and this is going to take a public key as well as the data that I'm going to pass through later on. This is what we're going to be passing on to the company in this case. So I'm going to be encrypting this data with my public key, and I'm going to be passing in my public key as well as all the values as a ciphertext and an exponent. Then I'm going to go ahead and dump that as a JSON and send that back. Now it says return serialized data. Again, this is an error. Apologize for that. This should say return serialized, which is also corrected as well. All right, next, let's start creating some data for this. Let's go ahead and get our keys from our getKeys method that we created. The data that we're going to pass is 24, 4, 6, and 1, and that corresponds to their age, their condition, and whether they're male or female. We're going to serialize that data. I'm going to store it as the public key, pass in the data with it as well, and then go ahead and save that as data.json, and data.json is what's going to go to the company in this case. And again, completely encrypted, so we don't have access to this data. I don't know what's sitting in it. I'll show you in a very quick second that the data is in fact completely encrypted. So what I want to do is I'm going to go ahead and open up data.json. You'll see this is exactly what the company is getting. So there's no way for them to know what's in this. So this is the public key itself. As I scroll across, even the data here, which is embedded in this variable called values, everything here is encrypted. So all these digits here is representative of that single digit 24, and then wherever the next list element starts, which is right here, this is representative of that 4. Only I know that because I'm watching it. There's no way anybody else will actually know what all this means. So this is what goes to the company, and the company is going to have to use their machine learning scalars against this to actually go ahead and build a model. So if we go back to our little example here, now we've encrypted the customer's data, which is data.json, and data.json is essentially what gets sent to company XYZ in this case. So we've gone ahead and done that, and that's what the serialization piece does. So now the next thing we need to go and figure out is, okay, well, how am I going to take this data? How am I going to deserialize it so that I can actually use it in mathematical computations and then apply my model against it to come up with some kind of an answer, which is going to be my encrypted result. So we're going to do that next. So now I'm going to create another file here called server calc, which is going to basically be my calculator on my server side under company XYZ. I'm going to go ahead and load some dependencies and go and get that JSON.data that they sent me. Now I'm going to open it up here as well. So this is what the company XYZ would see when they go ahead and print get data. So it's no different than what we saw in the JSON data.json file. Again, they're seeing a whole bunch of gibberish. This is completely encrypted data, so there's no way for them to decode this or make sense of this because they don't have the private key that sits with the client, and only the client can go ahead and decrypt this. So now the question is, how do we go ahead and build some kind of a model against this? So next I'm going to be building something called compute data. What compute data is going to take the data that we have, and it's going to take the scalars that we calculated in our linear model regression, which is what the my-coef in this case stands for. I'm going to extract the public key from the data that I got, because remember the public key is a part of it. Then I'm going to go ahead and get that public key and make it usable so that I can encrypt these numbers in a way that I can deserialize it and then use it in my calculations. What I've done is I've taken those scalars and I've multiplied each scalar by each encrypted element in the list, and I get an encrypted number object and then my public key in this case, which is what I'm returning. So now let's go ahead and get the ciphertext of the actual results that we generated, in which case it should be just a 1-by-1 vector because there's going to be no other list elements in this because I've multiplied and added everything together. So this is the answer. Now there's no way for me to know what this even means. This is what I'm going to be sending back to the actual client for them to use their private key to decrypt against, and it should give me the answer using that regression model. All right, now that I've generated some kind of an answer, the next thing I need to do is, again, have a serialize data function again, which is now going to send the encrypted result back to the client, in this case customer ABC. So I'm going ahead and I'm packaging up the public key again, and now the actual result, which was computed in the compute data function. Now what you're going to see is I'm actually going to go ahead and print this serialized result, and you're going to see that again it is completely encrypted. So this is the information that goes back. So it's a public key, the value, and then below you'll see there's an exponent of -14. This goes back to the client and they have to now use their private key to decrypt whatever this means. At this point, company XYZ will have no further ability to decrypt this now. All right, so going back to this example, what we've done is we've taken the ML model, we've taken the encrypted data, and we've gone ahead and created the encrypted result, which is what you just saw right now. What we're doing then is we've packaged this up as a JSON. The next step that you're going to see is we're actually going to go ahead and send this back to the customer in the form of answer.json. So we're just going to go ahead and create a very small little function or a little snippet of code that's going to allow us to take that serialized data now with the encrypted result that you saw that had the public key, the encrypted values themselves, and then the exponent. And that's going to go back to the customer as answer.json. So let's go ahead and see what that looks like. All right, so now you're going to go see that I'm building the main function here. I'm going to set my data file equal to my serialized data. Again, using the with open answer.json and writing it to a data file called answer.json. And then just closing it out with my if name equals main function. All right, so we're back in the customer file now. So now that the customer's got access to that answers.json data, now we're gonna build a function that's gonna allow them to load that data now. So I'm basically loading that data, calling it answer, and returning answer back. Now I need to build another function which is gonna allow me to take the answer file, load it, and now I'm gonna be able to go back and pull my public key out of this, and then pull the encrypted number from this as well, using the public key, the ciphertext, and the exponent. And if the public key that I get back from the file that the company sent me matches the public key that I have, then I'm going to use that private key to go ahead and decrypt the information. All right, and if this checks out, then we're going to go ahead and print our answer for this regression model. So before we do print it, again, remember, this was the original data, the 2461. I don't have the scalars here that were from the machine learning model because that came from the organization or the company that I sent my data to. I got back an answer, and now I'm going to go ahead and see whether this answer or not is going to give me some kind of a result. So let's go ahead and run this. and pull this up, and the answer I get back is $771. Now that doesn't seem out of line when we look at some of these numbers here. I mean, we do have numbers that are in the 700s and so forth, so 779. So nothing that is shocking when I look at it. I think what I want to figure out now is, now that I do have access to those scalars, so let's say this was the data that I'm looking at. I actually want to test whether or not the encrypted data did the calculations properly. So 771 is what this gave me when I use this encryption method. Let's just go ahead and let's go back to this file here where we know that this is sitting on the company's server. And again, remember when the company got these scalars, they were encrypted. So I'm just going to go ahead and drop these actual data values in here. So we know that data has these specific numbers. I know I have access to my coefficients here through the linear model. In theory, if I were to go ahead and calculate the coefficients in this linear model with these numbers, I should get that same number, 771. So let's go ahead and give this a shot. So I'm going to type in print, and we're going to go ahead and sum everything up, and we're going to sum up a list. So this is going to be a list of lists basically, or a list of elements. So data I times my co-fi for I in range len data. So basically it's taking the first element in here and multiplying it by 24, the second element and multiplying it by 4, and so forth. And we should get this number here as well, 771. So if I hit print, I get 771. So what that tells me is that it's actually done the calculation correctly. So in essence, what we've been able to successfully do is send this data in an encrypted format to an organization because we don't want them to know these numbers. They took encrypted data, they did machine learning against it, in this case a linear regression model, sent back an encrypted result. We decrypted that with our private key and we got an answer, which is kind of cool. So this actually works really, really well. All right, so let's take it from here and review what happened. So company XYZ produced answer.json. They went ahead and they sent answer.json to customer ABC. Customer ABC then compared the public key that was sent by company XYZ to make sure nothing was changed or modified or the wrong file sent, compared it to the public key that they had, and if they matched, used that private key to go ahead and encrypt that data, and then finally came up with the encrypted data, unencrypted data, which in this case was 771. All right, so let me just share a couple of final thoughts on this. First of all, just in terms of some of the concepts with PHE or partial homomorphic encryption, we didn't get into the concept of key rings. Key rings are basically a way for you to store multiple public and private keys. So for example, if I had customer ABC, but I had company XYZ and company DEF, I have the ability to just put all my keys in one key ring, and I can go back and search for that key ring based on the public key. So it just becomes a lot easier. I don't have to worry about managing multiple keys. So that's something that is available in the docs for you to look at. I've tried it myself. It's actually pretty cool. I just didn't want to go over it today because I thought it'd be a little bit overload with this subject. The second thing is, this is a glimpse into the future, though I would say it's not production ready at this point. I'm not aware of anybody who's actually put it into production. Right now, it seems like it's really heavy on the research side of things. So there's a lot of great work getting done by a lot of researchers out there. But I do believe that there's going to be a huge market for this in the future. If you wanted to go ahead and just explore some basic algorithms, I think this is a great way to do it today, just to sort of play around with it. But even just start learning and understanding a little bit about how data encryption works. Whether you're looking at database encryption or whether you're looking at data encryption, the way data travels, there's a lot of value in understanding how you can do that, especially as privacy becomes more top of mind with some of these organizations out there. Again, like I said, it's an evolving space, and with things like fully homomorphic encryption out there, there's so many more possibilities you can do. So you can get to more of the complex modeling. I've seen some research papers that actually have neural networks built off of FHE, which is kind of cool. And it has a lot more intensity in it as well. Things like bootstrapping / padding, which is basically a way to add, we'll say noise into your encryption model so that it's not easily something that you can go back and break or figure out. So there's a lot of cool things happening in this space. And my prediction is there's going to be a high demand for this over the next 5 years. Like I said, as privacy becomes more and more important to people and there's more organizations looking at it, a lot of investment going in this space, the ability to actually mine data that's very private, especially with, in organizations or in even countries for that matter that have really tight regulations against how data sharing practices look like. Encrypting that data is a really good way to get around it, but at the same time figure out how to mine it. But I don't think this is going to be production ready probably for another 2 to 3 years. At least that's my best guess at this point, but it could be sooner. And if it is, then that's something that I'm definitely going to jump on board on. So hopefully you guys enjoyed this video. If you did, please consider liking and subscribing, and I will talk to you next time. Thanks very much. Bye-bye.